Hello, everybody, and welcome back to Geography 341, Weather and Society. I'm Dr. Zach Hilgendorf, and in this lecture, we're going to be talking about annual energy variations and what drives those variations, and how we see those variations reflected across our world. Now, when we think of annual energy variations, we think of the seasons. So we're going to kind of talk about what the seasons are, what defines them, and what causes them in this video. And it's a really awesome series of pictures of this tree throughout the year. Down below, that is my source there, below my little talking face. But let's go ahead and dive into what these deviations are driven by. So here we can see the perihelion and aphelion positions of our planet. The aphelion position is on July 4th when the Earth is furthest away from the Sun. And the perihelion is on January 4th when it is the closest distance to the Sun, which seems a little backwards, doesn't it? Well, notice that the opaque plane that makes up Earth's orbital plane, you see that here, that is what we call the ecliptic plane. Now, despite Earth orbiting on a consistent plane, as we see here, the energy difference between the perihelion and aphelion positions only constitute about 7% of Earth's incoming solar energy. So this doesn't really account for or explain the seasonal variations that we see across our planet. So I'm just kind of cross that out, right? It's more or less joking aside. We need to talk about the concepts of axial tilt and axial parallelism. So while there can be no real definitive answer, it's thought that very long ago, something came and smacked Earth and knocked it off kilter, so to speak. Following this event, instead of rotating with its axis straight up and down, it leans. So as a quick aside, it is actually this large impact event that most scientists think led to the formation of our moon. It's kind of a massive chunk of Earth and rock and whatever was colliding with us kind of blasted off the side of our planet. We see this tilt, this axial tilt, at about 23.5 degrees off bubble, you'll say, which when you think of the north and south tropics, and that declination point that we just talked about in the last video, fluctuating between 23.5 degrees north and 23.5 degrees south, that's where it really comes from. Otherwise, it would just be right around the equator the whole time. So axial parallelism refers to the fact that the axis of Earth remains parallel to its previous position as the Earth revolves around the Sun. This means that Earth's axis always points in the same direction relative to its rotation around the Sun. We see that here. Notice that Earth isn't going like this on its axis, really, relative to the Sun. As it's orbiting around the Sun, the point with which the Sun is striking Earth directly overhead fluctuates because we're just off bubble from level as far as where our magnetic poles are. Notice how along the ecliptic plane, the axis is always at 23.5 degrees off center, no matter where it is along that plane. If we add some dates to that, like December 21st and 22nd, March 20th and 21st, June 20th and 21st, and September 20th and 22nd and 23rd, the story starts to develop a little more. Now, those of you who love the seasons and love seasonal changes and all that kind of stuff like me, you know that those are the dates of our spring and autumnal equinoxes and our summer and winter solstices, depending on which plane or which hemisphere you're in. So let's make a diagram. And this is one I would suggest if you're taking notes, and I hope you are constructing with me. So if you look at Earth here, that is our ecliptic plane, that line directly across. It's basically, that's the consistent position with which Earth is rotating on, if we think of like the orbit around the Sun. Next, we can see this imaginary line connecting our north and south poles. You see there. This line, 23.5 degrees off bubble, that's the line that our equator is relative to our ecliptic plane. You can see that bisecting the planet midway between the north and the south poles. This point is at 0 degrees latitude. The poles obviously are at 90 degrees latitude. This black line that we see here is the portion of Earth that is illuminated versus the portion of Earth that it's not illuminated. The portion that's illuminated is the hemisphere of illumination, but that point where it ends, we kind of call the circle of illumination. Here we can see a corresponding set of angles. You see those added right towards the middle there. These angles represent the offset between the line connecting the poles and the circle of illumination and are equal to 23.5 degrees. These angles here represent the degrees between the ecliptic plane and the poles and will always equal 66.5 degrees. So let's talk about some seasonal Earth-Sun energy relationships. First off, we're going to start with December 21st and 22nd. The time of, depending on which hemisphere you're in, we'll assume you're in the northern hemisphere so we can just be and talk consistently. Winter, the winter solstice. We look at our ecliptic plane here again, from the diagram we've got going on. That is our subsolar point. Our subsolar point is going to be at 23.5 degrees south latitude. That is our Tropic of Capricorn. What we call our December solstice, right? Declination is at 23.5 degrees south. It's the start of the astronomical summer in the southern hemisphere and the start of the astronomical winter in the northern hemisphere. Insolation intensity at the subsolar point at 23.5 degrees. If we recall, insolation intensity is found by the solar constant, which is 1,361 watts per meter squared, times the cosine of the zenith angle, or the solar constant times the sine of the sun angle. When it's striking directly overhead, and our zenith angle is 0 and our sun angle is 90, it will be 1,361 watts per meter squared. Now, what if you were down at 45 degrees south latitude, so 22.5 or 21.5 degrees further south? You're at 1,266 watts per meter squared. 66.5 degrees south latitude, 995 watts per meter squared. And if you're at the South Pole, 543 watts per meter squared. Now, if we flip and we're going northward, if we hit the equator, 0 degrees, so our zenith angle there. Not too much less than the solar constant, 1,248 watts per meter squared. But you'll notice as we go up further, it starts to very rapidly fall off. So at 23.5 degrees north latitude, it's 928 watts per meter squared. At 45 degrees north latitude, right about where we live, 499 watts per meter squared. And at 66.5 degrees north latitude, 0. If you think of the land, the phrase the land of the midnight sun or the land of eternal darkness, which is what the Arctic can be called from time to time, right now it's the land of eternal darkness during the winter months. There is no sun reaching it. Now, the other side of that spectrum, when it is the June solstice, then is the land of the midnight sun. You're always seeing the sun at that point in the Arctic. If we look at this from the perspective of day length, at 23.5 degrees south, the subsolar point, 13.5 hours of daylight. 45, 15.5 hours of daylight. 66.5, 24 hours of daylight. In the Antarctic, it happens too. Now going back up to the equator, 12 hours of daylight. At 23.5, 10.5 hours of daylight. 44.5, 8.5 hours of daylight. We think that's our shortest day of the year in the Northern Hemisphere. And at 66.5 and towards 90, 0 hours of daylight. Now, if we move to June 20th, 21st, the June solstice. See all these here again. Declination is 23.5 degrees north. Start of our astronomical summer in the northern hemisphere, astronomical winter in the southern hemisphere. Insolation intensity at the subsolar point is 1,361. We're just stepping backwards relative to what it was in the December solstice. So 1,266 at 45 degrees north latitude, 995 at 66.5 degrees north latitude, and 543 watts per meter squared at 90 degrees north latitude. It's the exact same numbers that we just saw, just flip-flopped, right? So here, 1,248, 928, 499, 0. Day length, same concept, 13.5, 15.5 at 45, 24 hours if you're in the Arctic Circle, 12 hours at the equator, 10.5 hours at the pole, or at 23.5 degrees south latitude, the Tropic of Capricorn, 8.5 hours at 45 degrees, the shortest day of the year in the southern hemisphere, and 0 hours of sun if you're past 66.5 degrees south latitude. What about if you are on the spring equinox, 20th to 21st of March? Well, our subsolar point is right there at 0. The equator. That's our March equinox. Declination is 0. It's the start of the astronomical spring in the northern hemisphere and fall in the southern hemisphere. So, what's insolation intensity at the equator on the March equinox? 1,361. I think we should be getting this by this point. I feel like I'm rather redundant. So 1,248 at the Tropic of Cancer, 962 at 45 degrees north, 543 at 66.5, 0 at the North Pole. Day length, 12 hours, 12 hours, 12 hours, 12 hours. In September, give you a hint. I'm just going to pan through that. It's the exact same thing. And on the equinoxes, it's the same in both the northern and the southern hemisphere. It's just the numbers in reverse from the equator. So to summarize, declination on December 21st and 22nd, 23.5 degrees south latitude, 0 on March 20th to 21st, the spring equinox, 23.5 degrees north on the June solstice, and 0 degrees in the September equinox. Day length, 12 hours along the equator during the December solstice, 0 hours at the North Pole, 24 hours at the South Pole, and variations therein. 12 hours across the globe during the equinoxes, both the spring and autumnal, or the March and the September equinox. Those numbers in reverse during the December solstice, or the June solstice, pardon me. We can see there for the September equinox. So what does that mean from a seasonal perspective? Well, in December, we have high noon sun and long days in the southern hemisphere, low noon sun and short days in the northern hemisphere. The exact reverse in the June solstice. Now, something very important to note, this does not apply to the tropics. The tropics are a different story because it's nearly constant incoming solar radiation, so they can support a variety of different things that we can't support outside of the tropics, so between 23.5 degrees north and south latitude. So in this video, we talked about what the seasons are, what determines the seasons, and what causes the seasons. We're going to talk in some of the next videos about some more of the variations, what drives differences across our planet. But I will see you in the next video, and I hope you have a great day.